Today we will talk about one of the most well, not the most important, but like one of the really important and relevant topic for you guys, which is synchronizations. How do you make sure that, let's say I have 4 threads going on, right? How do I make sure I synchronize? How do I make sure certain thing would have to happen before another set of things? So we talk about threading, right? And from the traditional view, right? And let's not go to threading yet, but let's look at process, right? Process is essentially consists of obviously the code the process has to run, the data that the process is operating on, the stack, and the process context. So what are the process contexts? These are the data register inside the CPU. These are the condition code of that particular line that the process is running, because like, let's say, for example, you add 2 numbers together, they result in a carry, then the condition code for the carry flag should be on. The stack pointer and the program counter, these are local to the process. These are local to the process, and they should be aware, hey, this is a line I'm running right now so that I can proceed forward. Then you will also have the kernel context. Why do you need that? Because first of all, you need virtual memory, right? You need to have your own address space. If you have file open, you have the scripted table, right? And the pointer associated with things like IO and syscall that the kernel control for you. Basically, these are more like a hardware level thing that the kernel has to open the APIs to the process, and the process are using it right now, right? And if you look at the code and the data and the stack to the right side here, right, to the right side here, these are basically anything that has to do with the memory side of things, right? When you run a program, obviously, where's your code? Might not be as obvious. When you run a program, where is the code that you're running? In the memory, right? It's not in the, it's no longer just in your hard drive as a file, but the code is now in your memory. You also have any shared library that you have to use, right? Those are a part of your code that you're running, so they are also in the memory, right? The BRK pointer basically points to the runtime heap. These are the heap associated with the runtime, and it can grow, right? The read and write data are also in there. Read only, for example, your code are read only. You're not supposed to edit your code when you run the program, because otherwise someone's attacking you for the most part. I guess I can ask you for an assignment to write a code that edit your own code, and then you can try to like attack your own code that way. Most of the time, yeah, you're not asking, like most of the time you're not doing that. And the program counter, for example, is pointing at this read-only data because it's a code, right? It's a read-only code that corresponds to this assembly line you're running. And you have the stack that you learn in system skill, which is growing based on how much local variable that you need when you have a function call. What are the function related data they have to maintain and things like that, right? And that's the process context. What happens you have threading? So is threading inside a process? Can I get a hands on who thinks threading is a part of the process? Yeah, right? Because you spawn a process, which is a program that you're running, and then you spawn threads inside the process, right? With threading, right? The process essentially becomes, I have the thread that I'm running right now, I have the code, data, and the kernel context. Then with the threading model, right, everything here looks the same. Then you still have the kernel context shared by all the threads, right? And now you have this main threads that run the main process, basically the main code that you're running. And they have the stack pointer, right? And they have the thread context, which at this point, it looks like a typical process context, right? But this is local to the main thread. So what happens when you spawn a new thread? I guess when I want to expand that question a little bit wider, right? Obviously not wider, more narrow. Now thread context has the data register. If I spawn the second thread, do they use the same register or a different set of register? It should be different, right? Because it's running essentially a different part of your code, so you can't share the register. There has to be a separate set of register to do that. All right. Do I have a separate register inside my processor on the same CPU? Not really, right? So that's why when I use the word context switching, it basically means that the physical copy of my register will be running the current thread. And if I have to switch, I have to switch the thread context out and put in the new context in for the new thread that you're about to run. All right. So here, when you have multi-threaded process, right? Each thread basically have their own logical control flow, obviously, but they run now two different things. They have their own independence. They should be able to run their own thing. All right. So the control flow is independent. They have their own logical control flow. But they share certain things. What are the things that they're sharing? Virtual address space, right? It's from the same process. So they are shared data. They use the same virtual address space. Thread 1, if you try to get the pointer address that belongs to thread number 2, virtual address will say, hey, that's an okay access. This is owned by the same process, right? So the permission check all pass. They have the same shared library. They have the same runtime heap, and the code looks the same, right? Because they came from the same process. It's the same C program you're running, so the code is all there. Then how? So when I said they share the same code and the data, right? Quick question: how can I know where thread 1 is running and where thread 2 is running? So let's say if I zoom this in, it's like a block of memory, right? This is like a first line of code, last line of code, like first line, and then the last line, right? How can I know that, hey, maybe thread 1 is running this part right now, and thread 2 is actually now here? What is local to the thread? Yeah. Even though they share the same code, they have a different program counter, so you know exactly where's thread 1 and where's thread 2. This is actually also efficiency purposes as well, right? They run the same code. Do I need to copy the code everywhere? No. Yeah, it's the same code, so I just put it there. Each thread has its own progress, right? So it can point to different part of your code, and that's fine. They don't share the stack pointer. As you can see here, the stack pointer are different. Why? What does a stack pointer do? What do we use it for? For the stack, right? Which used to maintain the list of function call that I'm doing so far. Is the thread doing the same thing, exact same? No, right? They are doing different things. They're calling different function right now. So you have to have a different stack pointer. They obviously need different data register and condition flow. So there are things that must not be shared, to be honest, right? As you learn more on the advanced, like graduate level classes or the computer architecture class, when we dive into the GPU, the graphic processing unit, you might realize, hey, sometimes the program counter can be shared, but it's a different model. For your CPU, they're different. All right. Then you can actually run thread in parallel, because why not, right? I have two PCs, they occupy different core. Different core have access to the same memory, because when you plug in the memory, the whole computer have access to that. So I can have this memory, right? CPU 1 and CPU 2 is running thread 1 is running thread 2, right? the code, let's say the code is right here, both of them have access to the code region. So I can run two codes at the same time, right? Using different program counter, and they both have legal access to the code, right? So let's say I have thread 1 and thread 2, and both of them need to run two events. It has to finish event A followed by event B. Let's say I want to print hello world followed by goodbye. Right? Event A is hello world, event B is goodbye. The order can be in any order as long as locally in each thread you follow EA followed by EB. So you can do thread 1, hello world, followed by thread 1, goodbye, followed by thread 2, hello world, followed by thread 2, goodbye. So that's a totally legit order. You can do hello world from thread 1, hello world from thread 2, followed by goodbye from thread 2, then goodbye from thread 1. So any of these order is okay. The only restriction that is not okay is you switch event B and A within the same thread, because as a program defined inside your program, this has to run before this. But across different threads, any interleaving is okay. Any questions so far? So this might answer some of the in-class activities we've seen so far when you have a bunch of things getting printed, right? And you feel like, hey, why is it printing in a different order? Because this happened. And when you run it again, it's like a totally different order, and that's okay too. Quick question, how do you debug this thing? You run it 10 times, it's a different order, right? It's actually a really hard topic. So you kind of need to know what should happen locally within the thread, and you debug that. And then you have to figure out how to synchronize between each thread, which is a topic we're doing today. So this is called the rest condition. It's not always a bug. If I intend for the thread to be having rest condition and no weird things happen, it's fine. Be mindful that in many cases that can also be a bug, because I need to make sure this thing has to happen before the other thing. Depending on the situation, this whole thing can happen in any order, but you might enforce certain things, right? So let's go with some high-level example, right? Let's say you have two threads, and both of them are operating on a shared linked list. So the program has one shared linked list for all the threads, right? What are some bad things that can happen? Quick question, how many lines of code do you have to implement if I want to delete a node from your linked list? Quite a bit, right? You have to do the for loop to find where you want to delete, then what? So let's say you want to delete this guy, right? You have to loop here, read what's in here, read what's in here, then make sure that this thing takes this value so it points here. So that way, this guy is gone, then you're free. All right, imagine two delete happen from the same two threads. From two threads. Okay, quick fun, right? So let me talk about one possible scenario. There can be many wrong things that happen. Let's go with one. So again, our linked list, right? Let's say the blue color is thread 1. Right now, thread 1 is doing this. It's here. It wants to delete this guy. So what thread 1 is doing right now, it detects, hey, that's where I am. I am basically writing this so that it points here. I am about to free this guy. Thread 2 comes in, green color, somehow get context switch at this part. But thread 2's code say, I want to access this guy. Can I? No, right? Because I read this. Where's the next one? Here. Okay, bye. All right. what's your intended result? I don't know. Your program definitely will have some intended result, but you need to tell which one should happen first, right? How can you enforce that? Wait, one possibility, right? What if you want to run them, make sure they run in parallel? I want to be able to make sure for the most part, thread 2 and thread 1 will happen in parallel. Because how many times you delete a node from linked list? Not a lot, right? You're gonna read it a lot. You're gonna access it a lot, but you don't modify the linked list a lot in many cases, right? So in that case, if I wait, it means that I don't have parallel program, which means that I cannot read in parallel. I cannot check if something is in my linked list in parallel. I cannot print the whole thing in parallel, right? So wait is a possible option for sure. That's a totally legit option, right? But it's serialized. So the keyword is if you do wait, it serializes your code so that you basically cannot really do things in parallel. On top of that, wait is a process management, right? So you can do what? Join, right? But when you join, you have to exit the thread. So it's kind of odd, right? So what you can do, what are the options? Login. So we'll talk about that in a bit, right? So we'll now talk about synchronization. So let's go with another example, right? I have a shared data. This is two threads, thread 1, thread 2, shared data. The code is there. If file exists, it's true, load the file. Otherwise, don't load the file. The other thread comes in, I want to set the file access to true. But right now it's false, right? So if the second thread come in and set the flag to be true, the first thread will basically read that and say, hey, I am going to load the file. So that's a possible scenario. What if I was here and the first thread gets to go first? Will I load the file? No, right? It's two totally different scenarios, right? So in this case, I'm not loading the file, but then the second thread comes in damn late, and that becomes true, right? So it's a two totally different scenario. These are things that can happen. I have a child thread that exit before even the parent can add the child to the job list. Because let's imagine a really stupid computer with one CPU. I don't have a multi-core CPU. I don't have fancy thing. I cannot run two threads at the same time. I spawn a child. I somehow pick the child that say I'm running this, and I exit. Let's say the first line of code of the child is exit. The parent's supposed to add the child ID to the job list. It's not done. So yeah, rest condition. What if the child thread reads something before the parent can change the variable unintentionally? So it's about the programmer intention. This can be okay. This can be okay. It depends on your intention when you program. That's the most important thing. What's your intention? Concurrent update to a shared variable. Concurrent means that it happens at the same time, then who beats to the shared variable will lose the update, right? Because the second update will win. Deadlock. What is the deadlock? All right, I'll give one example, right? The street in front of my house is ถนนบางแค right? And there's a section that's only one lane. This is like ถนนเพชรเกษม right? You know ถนนเพชรเกษม, right? It's like a long road to the south. And here's like a ถนนบางแค right? I just happen to be a one lane road. There's an outlet here. There's an outlet here. People love to turn right here. And people from, there's also another outlet here. People also love to turn here. What if there's a traffic here and there's a traffic here, no one can go? This guy in the front This guy at the front wants to turn right, and there's a traffic here as well. This guy, there's a traffic here, so wants to turn left. Can anyone make progress? Because the front guy blocked everyone else. So no one here will get clear. And he cannot go here because this guy blocked everyone else here. Now this means that that part cannot make progress, so there's no space for the guy to turn right, right? Deadlock. Deadlock means that no one make progress. And there's multiple ways you can resolve this. We're not going to talk about it today. We'll talk more about synchronization and sharing. So that's a separate issue that the OS has to handle as well. What if this happens? Imagine the left and right turn to be your shared resource, right? So here's a little bit more information on the high-low deadlock example, right? Let's say I have two persons, Alice and Bob. Alice is carrying a shopping bag and cannot put it down. Can only put it down once you're in the house. Let's say like the whole thing is flooded. You can't put the shopping bag down. It's like food, water. You have to go into the house before you put the shopping bag down. But Alice has the key to the house. That's the variable that you're sharing. Bob can open the door, but need Alice's key. So he's doing useless thing, which is standing there doing nothing, right? Now becomes more practical sense. Let's say I have a client waiting for the server and hey, I can close the connection. And then that's when I will close the connection. Server side has a buggy code that instead of sending the signal to close the connection, it first waits client to close the connection before sending the signal to the client, which makes no sense because by that point the signal will not arrive. But it's a bug. Deadlock as well, because the client will not close the connection, is waiting for the signal. The server is also waiting for the connection to close before sending the signal, so no one makes progress, right? You might not think that this is a easy thing to happen, but imagine team 1 write this code, team 2 write this code, right? So it's harder as the scale of your project gets bigger and bigger. And when you scale your project bigger and bigger, you need more and more parallelism, which means these things are likely to happen more often. So be careful, basically. Deadlock is a bug. So one way to deal with shared data is locking, right? So if a thread needs to update the shared data, lock them. When locked, no one else can access it. Basically, when you lock a shared resource, no one else can access it, right? Can I still have deadlock with locking? Can I still have deadlock when I have this locking mechanism? Let me give you a scenario. Let's say your shared data. Let's say you're about to go to the bathroom, right? You're sitting on toilet. You're finishing your whatever you're about to do. You look at a tissue paper, it's gone. But you lock the door. What do you do? Let's say you cry for help. What do you do then? Your friends are like nearby. Hey, I have tissue paper. Let's say you can't throw up. There's no space for you to throw in anyway. You lock the whole thing, right? So still with locking, be careful, right? Be careful. Deadlock can still, but if you don't do it properly, right? So for share variable in C program, now let's actually identify what are being shared, right? Because it's not as simple as I declare global variable and so everyone will use it, or like every stack variable as share, right? Because I mean, one thing you can assume, every single thing in the universe of the program is shared. What's the downside of that? Oh, upside, I lock everything. If I run the program, I am the only thread that can run this program. What's the downside of that? No parallel program. Because if I run, it means no other thread can run, right? So if I define everything is share, unlock everything, yeah, that's possible, but you serialize a program. There's not even any benefit of writing parallel program, right? So let's first define something. A variable x is share if and only if multiple threads reference some instance of x. Multiple threads. So the keyword is more than one thread need x. More than one thread needs x. Toward the end of this class, I will ask you guys, is this a strong assumption or can we make it weaker while still making it correct? But we'll go with that for now. We'll go with this for now. All right. Weaker means that can I relax this a little bit? So let's say in this case, I am going to have to log a bunch of things, right? Because there can be multiple variables that we share by multiple threads. Additional requirement that like what's the memory model for the threads? Because I mean people change the system and the hardware or like thing evolve. How many people in this in fun part before? How do you like Rust? You hate it, you like it. Why do you hate it? Too restrictive, why you like it? Because it's super restrictive, right? Rust makes an assumption on the way you program, and if you do make those assumptions, things will get really fast. So people like it, people hate it. It's like restriction that you put in on the programmer. So system change, language change, hardware change all the time. This depends on what's your assumption. We'll go with the standard assumption so far. How are the instances of the variable mapped to the memory? How do I map this thing to the memory, right? How many threads might reference each of these instances? So, sorry about animation bug again. This slide was not updated. My progress this morning is gone. I'll basically reiterate the animation. So let's say you want to identify what's shared, right? And right now you run two threads, thread 1 and thread 2. We already have the establishment that say, hey, the code and the data are shared. And there are some private stuff in the thread, right? Some data register and the stack, right? Each thread has its own thread ID, the stack pointer, the program counter, condition code, or the register, right? The remainder of the process context is shared. So that's conceptually is in your head right now. That's conceptually in your head right now. All right. These are conceptual things. Also, things like open file or install handler are shared. In reality, this happens. So you have shared code and shared data, which means that my code from thread 2 can access some variable in thread 1 stack. Because this is shared data, imagine this, right? This is code in C. You have a counter here, and you do counter plus plus. It just happened both threads need to run that line. So it means the counter variable is shared, right? So in that case, when you do the increment, they share the data. Even though counter is inside a local function, right? So data register can load something from stack of thread 1. It can also read and write data from the memory because these are shared. Let's say counter is here, right? In the memory, which is a part of thread 1 stack. Thread 1 stack, these, even though I said stack 1, these are a part of the memory, right? Now thread 2 have access to that. Yay, fun, right? And here's our example. We will take a quick break. Let's explain this example quickly, right? I have the main function here. I have the thread here. What does the thread do? Okay, first of all, I have two messages, right? Hello from Fu and hello from Bar is a character array. It's a string array. There are two strings, hello from Fu and hello from Bar. Right? I create a thread using pthread here. I create a thread. How many threads am I creating? Can someone tell me how many threads am I creating? Two threads. And what is the function call I'm doing? Again, pthread create also takes in the function you want to call. What's the name of the function you're calling? Thread, right? I have a function called thread. I'm calling that guy. What's the argument I'm putting in? I, which is 0 or 1, depending on the first thread or the second thread, right? And that becomes the input here, right? So let's look at the function I'm calling right now, right? Depending on the thread, I'm printing what? The ID. Where's the pointer to the ID? Where do I define PTR? Can someone spot that? It's somewhere in the code. Where did I define? Yeah, I have a global pointer. What does global pointer do now? Where did I assign? Yep. Message is a part of the main thread. I have my pointer pointing to the main thread, right? But the pointer is a global pointer, which means they are accessible by both threads. So I can do this. I can do pointer my ID. That's a totally legit example, right? And in that case, the first thread will say hello from Fu, the second thread hello from Bar, and that's okay. This is possible. You can run this code in C and it will be okay, right? Is that elegant? No, right? This is kind of like what sometimes we call it peer thread reference into the main thread stack, because the main thread has message that's in the stack because it is declared inside main thread. So that's definitely on the stack, which is supposed to be local to the main thread, but I have a global variable that points to that guy, right? So now let's declare a little bit more things. Definition of global variable, these are declared outside of the function. It's as simple as that. I have function call, things that are declared outside becomes global. Virtual memory only have one copy of any global variable. Why do I need just one copy? Because they all share. Everyone see it. If someone updated, everyone else should see the update. So I only have one copy. Why not? Local variable declared inside a function, each thread has its own copy on the stack, on the thread stack. Each thread has its own local instance of that guy. Local static variable, again, declared inside the function, right? The virtual memory contains exactly one instance of any local static variable. Why is that? What does the keyword static do? It doesn't change. So can I just declare it once and be efficient? I don't have to make multiple copies because it's not going to change. Everyone will see the same value, right? All right. Now with the memory mapping here, right? You see the global variable, I have only one single instance of pointer. I have a local variable like I inside the main thread, message inside the main thread. So .m means that it's from the main thread, right? Then I have my local instance from my ID. My ID is local to each of the subthreads, thread 1 and thread 2, right? And then also have a local static variable count CNT. All right. Now let's do some quick analysis, right? Again, a variable is shared when they are shared by what? More than one thread. More than one thread can access that guy, it means that's a share. So which variable are shared? Let's look at pointer. Is shared by the main thread? Also thread 0 and thread, everyone can access pointer. Right? How about CNT? Main thread, no. Thread 1, thread 2. I declare the main thread, right? Not shared by thread 0, not shared by thread 1. Message, this is the tricky part. Message is the local in the main thread, but it's used by thread 0 and used by thread 1, even though it's not declared in thread 0 and thread 1 because of pointer. Because of pointer. All right. Now my ID dot P0, but my ID inside P0 only used by P0, not used by P1. All right. Is it clear now? The key thing is this guy. Even though I declare that in the main thread, it's used by thread 1 and thread 2, so they are shared. Right? So in this case, again, pointer count message are shared. Right? Pointer count, sorry about this. Let me animate this. I and my ID are not shared. So share, share, not share, share, not share, not share. Okay. Now to synchronize, right? Obviously, you want to share data. Share variable can be useful. It can be useful in parallel program, right? But also it introduced a lot of bugs, right? Especially synchronization error. Imagine that scenario earlier, right? Because and I said thread 0 and thread 1 and thread 2 can happen at any point in time, which means that I run this thing 1,000 times, I'll see different results. Imagine you try to debug your code in Skill, but the second time you run, it doesn't behave the same way. The third time you run, it also doesn't behave the same way. Fun, right? So this can be nasty. Now we will do a quick break. But before we go, I'll leave the code up here. It's a counter. It's a simple counting program, basically. But it does have some fun thing with this guy. It's a counter that counts from 0 to something. Okay? So I'll leave the code here. Let's do a 10 minutes break. We will be back at 11. All right. So if you look at this program, what's shared? What's like one of the main things that's shared here? Count, right? This guy here. I run it twice. I get 2 different results. Why? Why is it sometimes okay and sometimes not okay? Okay, quick question. What does thread do? It increment count based on the input from my argument right here, this guy. If it's in this case 10,000, I will loop 10,000 times. Every time I loop, I add 1 to count. But that's for one thread. When you look at count plus plus, when you look at count plus plus, what are the actual operations to the memory you have to do? Let's say this is like count. Read from it, then add 1 to that, then what? Right? It's actually 3 operations. Read, increment, write it back. All right. What if I read it and it says 10 for thread 1? I increment to 11 I haven't finished writing. Thread 2 comes in and read from it. What do I get? 10. Thread 2 increment to 11. Both of them try to write 11. What's the final result? What's the true value that you get? 12, right? So how do I fix this? Where do I lock? CNT count, right? If I can lock that guy, whenever I'm about to increment, is that okay? So first thing first, the goal is I want to be able to lock things, but lock for the least amount of time. Imagine this, right? Let's say even use the restroom right there. Every time I go in, I lock the entire thing. That'll be annoying, right? That'll be like, because there's multiple stalls, people can use them. I am not supposed to lock the front door. A more extreme example, if I want to lock the entire program, I want to use the restroom, I lock this entire building. It's about that extreme, right? So the goal is I should only lock things and just that thing that I need, and that's it, no more. All right, because the more I lock, the slower is your program. Okay, so how do we fix this? So let's actually now, as I said, right? If I zoom into this and you look at the assembly code of this guy, it's basically read, increment, this is +1, and then put it back. This is like read the variable count, right? Add 1 to that and then write count back. Any questions so far? Yeah, exactly. I want to make sure I got this, right? I want to got it. Whenever I need to do something with count ++, I want to protect that thing. All right. Okay. This is concurrent execution, essentially. And the idea is any sequentially consistent interleaving is possible, but some, like basically the first sentence means I can run in any order between any two threads or more. They are possible, but some will give you unexpected results. And they are still going to be called sequentially consistent by the processor because I define it that way. From the hardware point of view, there's nothing wrong with this assembly code because the programmer gave this code to me and I do exactly as what I command. I'm commanded to do, right? It's not the hardware fault, it's the software programmer that should lock this, okay? That's what we call sequentially consistent. When we go into deeper concept in architecture, we'll define what is sequentially consistent, but not in this course. Not in this course, because it's more related to things like multi-program, multiple CPU, how do I guarantee consistency and coherency and things like that. So in this case, let's say RDX1 is RDX of thread 1, RDX2 is RDX of thread 2, right? And CNT is count. And if we, let me go back one more slide. What is RDX? RDX is the variable count that you're reading, right? That you are reading. You basically have count ++. The first thing you do, put that value into RDX. Register is local to each thread. So thread 1 has its own version of RDX. Thread 2 has its own version of RDX. All right. N sub I means that I'm doing instruction N for thread I. So H1 means it's instruction H for thread 1. L1 means instruction L for thread 1. So what I do here is I load 1 into the first thread. The first thread now has 1, right? Because it looked at count. My bad, not 1. Originally count is 0, right? Then the first thread load. Read the value from count, which is 0, so it has 0. Use update. I update 0 to 1. right? 0 now becomes 1. I store, I put the data back. I write this 1 back to count. Now count has 1. Then I finish. Thread 2 comes in, right? They say, hey, I want to read. I want to load, basically load. Whatever I see from count, which is now 1 into my register, update, store back here, right? Store back here. And then at the end of the day, everything is okay. That's a totally possible interleaving between thread 0 and thread 1 and thread 2. In reality, in Eclipse, it's even more possible interleaving that are non-sequentially consistent are possible because we relax the assumption to make your CPU faster. Again, we're not learning this in this course and this semester, all right? But here, one thing I can do is I can label what I will call critical section. Critical section, sorry about this. Critical section is, I'm not supposed to have this animation. Basically, the only thing I should change from this slide and the earlier slide is the coloring. Critical section for thread 1 means that I should be the only guy doing this thing. No one else supposed to come in and execute the code that modify count. Then the blue thing is for thread 2. It's as simple as that. Now, if you do this, you see that there's interleaving here where I try to update RDX of thread 1. I count from 0 to 1. Before I can write it back, thread 2 comes in, hey, I want to read that. What is reading? 0, because I haven't finished update. Wait here. Thread 1, read, update, write. And here's thread 2. Thread 1 finished reading, finished updating, haven't finished writing. Thread 2 comes in. I want to read. What is going to read? What will thread 2 read here? 0. Because thread 1 hasn't finished the update. So thread 2 comes in, hey, what's the value? 0. Thread 2 then update and store. So at the end of the day, instead of 2, you get 1 for count. Right? How about this interleaving? Is this okay? Originally, everything is 0. I load 0 to here, right? Load. L1 is load. H is not loading yet, right? Then I load what? 0 into thread 2. I load to thread 2. I update to 1. Then I store, right? The value 1 here. I then update this to 1. This is 1. I store the value here to 1. So this is also wrong. Right? Now we're going to learn the concept called the process graph. Now you just learn a concept called critical section. Critical section are things that if I start doing this, if I start to run this block of green, green thing, no one supposed to touch things I need to access inside that block. That's why we call it critical section. I should be the one who do this. All right. Now, a process graph would depict a discrete execution state for any number of threads that you're running. So we will draw a graph for 2 threads to simplify things. Each axis corresponds to the instruction that you are doing. Because you run one instruction followed by the next, followed by the next, followed by the next, you can definitely plot them. And the point would correspond to a possible execution state. Because you have 2 threads. Thread 1 can be at instruction A. Thread 2 can be at instruction B. So in that case, it will be a different instruction. Like L1, S2 in this case will basically say that thread 1 has completed instruction L, which is a load, read from count. And thread 2 has completed S. I finish writing back to count. S is store, load, and store. All right. So here, again, thread 1, right? Load, update, store. So that's the critical section for thread 1. Thread 2, load, update, store. So this is the critical section for thread 2. Thank you, sorry. When you finish running, you start, basically when you begin, you start here, right? Bottom left is where you start. You keep going up. And you definitely have to finish there. Why? Well, each thread has to finish the sequence HLUST, right? Load, update, store, and then do whatever it has to do afterward. Thread 2 is the same thing. Each of the gap here represents I finish one instruction. So if I run this on a CPU, it means I can only move horizontally or vertically. I can't move diagonally because that means magic. I run 2 threads at the same time. All right. So a trajectory is a sequence of legal state transition, basically legal move from bottom left to the top right, such as this. Right. That's it. Run 2 threads, finish it. This is legal because even though there's a critical section, my program doesn't say so, so I'll keep doing this. And any order, any permutation that are legal move is okay. I can move here. I can move here. I can do this. These are all legal moves. Now, what's our goal? Our goal is to make sure I can declare what is illegal. Because if I can declare what's illegal, it means that my program should be correct at the end. All right, so that's our goal. So you know that these are the highlighted part are the 2 critical sections, right? Load, update, store. So those, if I do this, I should finish this in one go. So LUS form a critical section with respect to the variable count that you see earlier. The instruction in the critical section that has to access the same guy should not interleave. Basically, if you're about to do anything like load, update, or store by the 2 threads at the same time, that's not legal. Only one of them can move. So once you have a critical section, I can say that region is not safe. And that's it, right? That becomes the place you cannot walk in, which means that I can walk like this. And that's okay, right? Why is that okay? It means the first thread, load, update, store, followed by the second thread, load, update, and store. And that's okay, right? That's totally okay. I can do this. Start, load, update. For the second thread, I don't finish the whole thing. Then I do H1 because it doesn't have anything to do with the count, right? Then I keep going up here. And that's okay too, right? So a trajectory is safe if and only if it doesn't enter into that region, the region where the critical section collide. Right? Okay, basically this simplifies a lot of things. Once you have this process graph, you just make sure that you don't go into that. And it's simple for a really tiny program you saw earlier. What's the problem now? What if your project is a design Twitter? What would be my process graph? It's going to be somewhat complex, right? But now, once you can define this, you know where it's not safe. In reality, you have to be kind of do this for a bit and you get used to it, kind of thing. A trajectory is correct with respect to that shared variable if and only if it's safe. Something like this is okay, right? Something like this is not. Because you try to load update and then the second thread come in, I want to update too. I need to finish store before the second thread can load and update. So now, let's look at the share variable, right? So the focus of us, this is the same program, so I'm gonna just go through quickly. The only difference is let's analyze what's share. You will see that this is share and iter is share, right? And iter is share. What about iter that's not problematic for us? Am I updating iter at all? No. So multiple people can read from it. It's fine. No one modify that. So there's no that it's going to be consistent regardless. Now we will transition into how do we enforce this? What we call mutual exclusion. What does exclusion mean? To not include, right? So this is kind of like a mutual agreement between multiple people that if I try to do something here, no one else should do it here. All right. So the goal again is to guarantee safe trajectory, right? The idea is simple. I want to synchronize the execution of threads so that they can never have any unsafe trajectory. By having this mutually accessible exclusive access to one thread for each critical section. So when I say critical section, I make sure only one thread can enter that and exit from it at the same time. All right. These are classic solutions to do that. One of them is called mutex, the other one is called semaphore. We'll go into the detail of both of them. There are many other approaches like conditional variable to pre-threads, monitor in Java, and the ownership system in Rust. We'll learn the third one a lot in a different class. You don't have to suffer through that right now. Let's suffer through mutex. So mutex is the Boolean synchronization variable. What's the Boolean? True or false, right? Basically, I define it this way. A lock has a value 0. Unlock has the value of 1. I can then define an operation swap on a reference. This is a pointer. Right? I have a pointer. A swap between A and B will swap A and B, but everything happened together. When I have this bracket in C, this is the magic by the hardware and the OS would make sure that this will happen at the same time in one single transaction atomically. When I said atomically means that if I begin that thing, I will finish without any bugs or any weird scenario coming from another thread trying to access A and B and modify that. Nothing weird will happen. If the OS or the hardware detecting any weird thing like parallel thread trying to access the same thing, one of them will finish, the rest will fail and redo it again. So it basically keep doing it until it succeeded. If weird thing happen, only one will succeed, the rest fail, retry. All right. Then I have the operation called lock. The mutex. Let's say I want to lock a mutex called M. The way I will implement the lock function is I have a loop. That inside I want to swap the state of M from unlock to lock using a swap function. I want to swap the state of M. If it's unlocked, I will lock them. If it's already locked, I'll wait until someone unlock that and lock them. Unlock means I change that to unlock. It's as simple as that. So I can implement mutex this way. Now, we'll talk about how do we use it in a bit. We'll talk about how do we use this in a bit. So here, if we have mutex, how will we fix this? Question, can I lock right before CNP++, then unlock afterwards? Because based on my implementation of mutex, right, I can lock it only if it's unlocked. If it's already locked, I cannot really access them. The swap will keep retrying until it's actually unlocked. And then I swap the state from unlock to lock. The nice thing about mutex is because that's the case, only one person can lock this thing. Because if it's already locked by someone else, I cannot lock it again, right? It means that if I declare a mutex on any part of my code, only one guy can access that. That thread will lock it, and no one else can access it until that thread again unlocks the mutex. That becomes a barrier, basically, that only one thread can come in, no one else can. All right. So if I put mutex around this, oops, sorry. So first I can do this. pthread mutex underscore t. I declare a mutex with no special attribute. This basically allows like a mutex that you can use for pthread. Then again, that's my loop, right? With this is the original code. I just do count plus plus. You can make it simple. This is it. You initialize mutex, then lock and unlock. That's it. That's it. So the way you use mutex is simple. If you know that any region in your code is not safe, like it's shared by multiple threads, and you need to lock them, put the lock before, put the unlock right after. Yes. Oh, okay. All right. Is it simple? Yes, and also no. Because in the future, let's say you have a really complicated program, you might forget to lock things, or you might unlock things twice, or things like that. It can happen. Or you can have a deadlock. Lock one thing, lock another. Like the restroom example, your shared resource is the toilet and the paper roll. You lock both things, but you forgot that, well, someone better update the paper roll if it's empty, right? So once you have a bunch of shared variable and you want to make it as fast as possible, you want to be careful. But if you're too careful, when you lock too many things, it's going to be slow. All right. Now here, with the good count, right, you will see that the time it takes go up. Why? So bad count is really quick. Bad count is really quick. Good count is a lot slower. Why? Yeah, basically, once you are doing count plus plus, only one thread can go. And it just happened, if you look at this program here, right? Where is the majority of the work that you have to do? Inside the loop. Inside that loop, right? If you have 10,000 items, you're gonna spend most of your time in there. So you basically lock the whole thing, right? So that's why I said if you lock, it's gonna be slow down. So that's something you have to be careful about. Now, when you have this lock, right? When you have this lock, so you have new instruction, lock and unlock, right? The lock and unlock instruction, make sure, right? Once you lock this, no one can access the region that dictated by the lock in another thread, which means there's no way you can go in. You can't go up here. You can't go up because mutex dictates that no one can take the lock at this point until I unlock it first. So I need to go to the right, and that's the only option. Mutex is an invariant that basically create a forbidden region in your process graph that you can't walk in. So this way, You can go in here, right? But you can do this. Oops, sorry. Do this. And let's say if I put the value next to the dot that represents the value of mutex, which is true or false, right? Lock or unlock. It can only be in lock or unlock state, which in this case, when you lock them, it goes down from 1 to 0. And you can't lock it again. If you lock it again, it goes from 0 to -1, which is not legit. Like you can't do that. So mutex enforce the case where the mutex value itself becomes lower than 0. Now, the alternative option is what we call semaphore. Instead of a true or false, lock or unlock, we use non-negative global integer to synchronize your share variable. How do we do this? So I have an operation called P. P of S will check if S is non-zero, decrement this by 1 and return. If S is 0, stop the thread that do P of S until S becomes non-zero, then the thread can keep going. Then you have the V operation will increment S. Think of P and V as lock and unlock, but in this case, it go up and down. All right. And let's say the variable is shared by multiple people, and you can share up to 3. Let's say instead of locking and unlocking, you say, hey, this guy can be shared by up to 3 people. Then you can start with 3. And let's say you have 10 threads in here. Thread 1 comes in, that go down to 2. Thread 2 comes in, go down to 1. Thread 3 comes in, go down to 0. The rest of the thread has to wait until the thread using it called V, which increment from 0 to 1. The invariant is the value of S has to be greater or equal to 0. If it starts with 4, it means I can have 4 concurrent threads, and I would limit just to that. To implement, you can use atomic operation as well. While S equals 0, wait. Otherwise, decrement S. For V, increment S. So these are simple. I put the bracket in to force atomic operation, force to make sure everything happens in one go. The OS kernel guarantee that that whole bracket is atomic. And here is how you can use it. You can do include semaphore.h, and then you can call semaphore init. And then T is called semaphore wait. The V is called semaphore pause. So you init the semaphore T as a type, right? And you put in the value like 2, 2, 3, 4, 5, depending on what you want to use as the initial value here. Okay. Let's say I use 2 means that 2 can enter. If I put 3, the counter will start from 3, then 3, 2, 1. That will be the limit. And thread can use semaphore to notify other threads that something can become true. There's a counting semaphore, which is what you see. And you can use binary semaphore to notify other threads as well. So we'll use the producer-consumer problem to motivate why you might want to use semaphore in some case, right? Think of it as this. I have a shared buffer between 2 threads. The first thread produces the output. I need to put it in the buffer so that the consumer thread take it. The condition is this. If the buffer is empty, the consumer thread is not supposed to take anything in. If the buffer is full, no one should be produce anything into that buffer. All right. And we will start with only one thread that are producing value, only one thread consuming, and only one slot buffer. Okay. Simple. I only have one slot for the buffer. Only one guy producing something. Only one guy taking something from the buffer. This is a common synchronization problem because I need to make sure if I produce something, that slot better be empty. If I want to take something in, that slot better be full, right? And this can be something like multimedia processing. If I want to draw something on the video frame on my monitor, right? I need to have the GPU write the data, say, hey, show this color on this pixel. Then the consumer, which render the whole thing, takes the color value and show the actual color. And we do this a lot in the OS, in network, everywhere. Everywhere in a computer, we use this. Now, let's say I will have the state called full and empty for the buffer. All right. We just need to maintain two semaphores, one called full and one called empty. If the buffer is empty, full semaphore is 0, empty semaphore is 1 because it's empty. The other way around, if the buffer is full, the full semaphore is 1, the empty semaphore is 0. Now, here is how we can use it, right? So we have the producer and the consumer. You have the struct that deal with the full and the empty semaphore that are shared. Then you init the semaphore, one for the empty, one for the full. Right? Again, we need two semaphore. Why do we need two semaphore? Because the producer just need to check whether it's empty or not. The consumer only has to check if it's full or not. They're kind of like a separate thing. So it's better to have two separate semaphore. Now, I can create the thread and then just do the join, right? Initially it's empty, so empty is going to equal 1, full semaphore is going to equal to 0. On the producer thread, let's say it's a GPU that's about to say, hey, put this color on this pixel, right? Put this color on this pixel. I put this color on my share buffer so that someone else can take the color value and draw them on my monitor. So that's a producer. To make sure that it's actually empty, I would put P here, P for the share empty. P for the share empty will do what? P decrement, V increment, right? So when I do P and share empty, I decrement empty to 0. I put the item in, then what? Well, first of all, at that point, no one else can use P empty because P empty is 0 already. If I do P empty again, it tries to go down from 0 to 1, -1, so that's not possible. If I do P empty, it's gonna wait until P becomes 1. The second thing, I cannot do P full. I cannot do P full again because full is already 0. P full wait until full becomes 1 before I can use it. It means that producer, at this point, producer is the only guy who can do anything because consumer is waiting for what? Consumer here is waiting for the full to be 1. Now, look at this. The code, now I put item into the share buffer, and in the producer, what do I increment? Do I increment empty or do I increment full? I decrement empty, then increment full. That allows the producer thread to communicate to the consumer, say, hey, if you need full, now it's there, consume it. On the consumer side, the first thing I do, I check if the buffer is full. Once the consumer puts something in, that becomes true. So you read the item. Then you don't increment full, you increment empty because you notify the producer, hey, now it's empty. All right, is it more clear now? All right, now we can use the same model for any number of producers. Let's say I only have one single buffer, right? The same thing. But I have 10 producers. I can use the same exact code because only one producer can put item in the buffer. If it's full, only one consumer can take from it, and that's it. Now, if I want to make a buffer of size n, right? Because I mean, a buffer of size 1 is not really useful, right? Now, if I want to use the buffer of size n, what do I have to fix? The initial value, right, from initially is 1 empty, because we only have one buffer of size 1, n empty. So now you can keep putting in until becomes 0. And if there's something in there, full will go up, which means the consumer can start processing it. All right. Now, the only quick thing, right, is you can use semaphore to communicate the number of slots. Can I put it in? Can I take things out? You might want to use mutex to protect the buffer as well, because you want to make sure buffer is shared. You want to make sure two threads doesn't happen by accident, update the same thing at two different things at the same time. So you need one more mutex to lock the buffer. So now your semaphore becomes from 0 to 1 and 1 to 0 to 0 to n, n to 0. And that's it. That's all I have today. Please check the in-class activity. If I recall correctly, this should be the last in-class activity before we fully transition to your project one.